everyone, welcome to BCP Med. In this video, we're going to be taking a look at Lewis dot structures, how you read them, how you put them together, and what all the different portions of the Lewis dot structure mean in terms of the chemical properties associated with a given molecule. Let's go ahead and get started. A Lewis dot structure is a diagram which contains information regarding the connectivity of different atoms within a molecule, the number of bonds present, lone pairs, and of course, what atoms are actually present inside of a given molecule. A Lewis dot structure might look something like this, which represents the Lewis structure for carbon dioxide, or CO2. As you can see, the molecular formula, CO2, is clearly represented with one carbon and two oxygen atoms, and the bonds and lone pairs are also indicated. The bonds are represented as either single, double, or triple lines to represent the kind of bond, a single, double, or triple bond, between the atoms. Each line represents the two electrons present in a covalent bond and shows the connection between which atoms are participating in the bond. So in this case, the C is double bonded to two different oxygens, which are themselves not bonded to each other, only to the carbon. Often, but not necessarily, simple inorganic molecules are going to have a central atom to their Lewis structure, which in this case is carbon, and that central atom will be connected to a series of peripheral or valence atoms, which are bonded around the exterior of that central atom. Oftentimes, though not necessarily, peripheral atoms tend to be more electronegative and make fewer bonds than the central atom. So in this case, oxygen being more electronegative would be considered our peripheral atom. As you can see, it is around the outside of the carbon, with two oxygens being more than that single central carbon. Finally, the lone pairs on atoms are going to be represented as dots, which are usually going to be paired, hence lone pair, and located around the outside of the chemical symbol for the atom inside of the Lewis dot structure. Ultimately, our goal is to be able to put together a Lewis dot structure for any molecule that we come across, and to do that, we're going to need to have some tools in our toolbox. The first thing that we're going to need to be able to do is choose the central and peripheral atoms based on the molecular formula that we are given, which will give us a general outline of what the Lewis structure will look like. The first thing is choosing the central atom. So generally, central atoms are going to be singular in number, which means there's only going to be one of them, and they're going to be less electronegative. They're also typically going to be able to form more bonds, which is why they're central. They're going to be able to branch out and form bonds to several different peripheral atoms. Those peripheral atoms, on the other hand, are going to tend to be more numerous. There's often going to be more than one, which is why they're on the outside. Although we can have one of several different kinds of peripheral atoms at the same time. Peripheral atoms also tend to be more electronegative. We can often look at Lewis structures or covalent bonds in general as the peripheral atoms attacking the electron density of the central atom. The more electronegative atom is trying to steal away the electron density, and so they are found on the outside. They are also typically able to form less bonds and only usually form single or double bonds. Some common central atoms are going to be boron, carbon, nitrogen, phosphorus, and sulfur, which are towards the left-hand side of the nonmetal series on the right-hand side of the periodic table. So our left side nonmetals, like carbon especially, are relatively not electronegative, and so they're easily attacked by other atoms for their electron density. Some common peripheral atoms include the halogens, F, Cl, Br, and I, which are all quite electronegative and only form single bonds, hence they tend to be peripheral, and oxygen, which is often double bonded or present as an OH group. Oxygen is very electronegative, second only to fluorine, and will tend to attack many different kinds of atoms, forming combinations of double and single bonds within a given molecule. Now, a special case is going to be hydrogen, which is always going to be a quote-unquote peripheral atom. Hydrogen can only ever form one bond and is very small, so it won't ever be a central atom. It'll always be found around the outside of a molecule, even though it is relatively not electronegative. So now let's go ahead and take our first steps towards putting together a Lewis dot structure. Generally, the first thing will be to identify the central and periphery atoms using the noted trends we talked about in the last slide, and then we're going to want to draw the base valence picture for each atom. We're going to want to put the number of valence electrons around its chemical symbol. Then we're going to want to arrange all of those peripheral atoms around the central atom with their electrons included. And we'll look at an example of how to do this in just a moment. If it's applicable, though, you want to immediately match up any unpaired electrons from the peripheral atoms to a single electron in the central atom, whether or not it's paired. You may need to split the pairs on a central atom, in fact, in order to match unpaired electrons. So what does this all mean? So let's go ahead and look at the example of ammonia. So ammonia, our molecular formula, is going to be NH3. What we want to do first is identify the peripheral and the central atoms. So, just like I said, hydrogen is always going to be peripheral because of its size. So as a result, H will be peripheral and N must be central in this case. Having identified the central and periphery, we want to go ahead and draw the base valence. So that is going to look like this. Nitrogen has 5 valence electrons. Electrons like to pair up, so to speak. So we're going to go ahead and draw 2 sets of pairs and 1 unpaired electron for nitrogen. Because you have 5, it's an odd number, you can't force an extra pair. So we have 2 pairs and 1 lone electron, and hydrogen, having only 1 electron, can only go ahead and form that, or can only have that 1 lone dot. Now, the third bullet here on this slide is going to be, if applicable, match unpaired electrons from the periphery to single electrons in the center. So we're going to do just that. The peripheral atom is hydrogen, and it does in fact have an unpaired electron. So we're going to match it to electrons in the nitrogen. How are we going to do that? Well, it's going to look something like this. We're going to split some of the pairs in the nitrogen and use the already lone electron in the nitrogen to pair up with the hydrogens. So there's 3 hydrogen atoms in our chemical formula, NH3, and so we're going to take the first hydrogen and pair it with the unpaired electron in nitrogen, and then we're going to split a lone pair in the nitrogen and pair it with 2 hydrogen atoms, which are the remaining H's. And then we get this picture. We see N is paired, we have the N electrons are paired to their hydrogens, and there's 1 leftover pair, which is going to be known as a lone pair. Oftentimes, there will be no unpaired electrons in a peripheral atom, such as in oxygen or sulfur, which don't have any unpaired electrons. If this is the case, if there are no unpaired electrons, what we want to do is match quote-unquote empty spaces in the valence of peripheral atoms with pairs from the central atom. Let's go ahead and do an example to clarify what we mean by this. So if we look at the CO2 molecule, our first step is to choose the center and the periphery. Now, we've already looked at CO2, so carbon is probably going to be central because it's less electronegative and singular in the molecular formula. Oxygen is probably peripheral. It's more electronegative, and there's more than one of it. So in this case, C will be central and O will be peripheral. So we want to go ahead and then draw our base valence for the electrons, but we want to note how the carbon pairs will move as we rearrange things. So we're going to draw our base valence, but when we go ahead and actually put together our first steps for the Lewis dot, we're going to need to move pairs, and that's totally fine. So our base valence is going to look like this. Carbon's going to have 4 electrons, and oxygen is going to have 6. Notice oxygen has no unpaired electrons, but notice there's a gap on the right-hand side of the oxygen atom as we've drawn it, where 2 more electrons could nicely fit, right? Every atom wants 8 electrons, so to speak. So we want to fill that gap in the oxygen valence, and we're going to use carbon's electrons to do that. So we're going to go ahead and move the carbon electrons into those spaces of the oxygen atoms. We're going to put the peripheral oxygens on the sides of the carbon and then move the central atom electrons into those empty gaps. That way, we can sort of see how the carbon electrons will start to complete the valence of the oxygen to give it 8 electrons total. So when we go ahead and draw our Lewis structure after having ordered all our atoms into the correct positions, the first bonds we're going to want to draw are going to be to connect the unpaired electrons between the center and the peripheral atoms. Then we're going to want to connect the lone pairs from the central atoms to form the bonds to the peripheral atoms that have those blank spaces. So first we want to connect unpaired electrons and then fill in the quote-unquote blank spaces. So what's that going to look like? Well, we started with ammonia, which has our unpaired electrons. We're going to connect each of those with a line. So that is going to look like this, right? The pairs of electrons from H and N are going to become a dash, which represents a bond, right? Remember from our earlier note that the bonds in a Lewis structure represent 2 electrons, which are a single bond. So in this case, those pairs become single bonds, and that leftover pair on the nitrogen that has no associated H is just left over as its own lone pair. Now, if we look at carbon then, it has no, or carbon dioxide, it has no unpaired electrons, but it does have those empty spaces. So that's our second step. We're going to go ahead and use those lone pairs in carbon to fill in the blank spaces in the oxygen with a chemical bond. So that is going to look as follows. We're going to just take those electrons from carbon and make them into a dash, into a solid line representing a single bond. Notice that there is no electrons moving in the oxygen in this first step, right? So unpaired electrons first, and then fill in those blank spaces. So this is where things are going to start getting a little bit tricky. At this point, if any of the atoms that you have drawn do not have a full octet, which means they don't have 8 electrons either in their bonds or their lone pairs, you need to move some electrons around into new bonds to form full octets. Now, specifically how we're going to do this is we need to form higher order bonds. We need to form double and triple bonds between the central and peripheral atoms. These higher order double and triple bonds are going to be formed by taking a lone pair from one of the peripheral atoms and then moving it into a bond with the central atom. So what is this going to look like practically? Well, let's say we have our CO2 model, which we've been working on. In this case, the oxygen atoms each have an octet. They have 6 electrons in their lone pairs and 1 bond for 2 electrons, making a total of 8. However, the carbon atom is electron deficient. It only has 4 electrons in its bonds. So we need to somehow move electrons from the oxygen into the carbon so that the carbon also has an octet. We're going to go ahead and take 2 electrons, 1 pair from each oxygen, and move it into a new bond. And what that's going to look like is the following Lewis structure on the right. Now we see how we took away one of the lone pairs on the oxygen and added a new bond. We basically just moved it over. Now the oxygen still has 8 electrons. Nothing has really changed. It has now 4 electrons in the bonds and 4 in lone pairs, still giving it 8. However, carbon now has 8 electrons, and it is quote-unquote happy. So the strategy that you want to take with this is essentially to go ahead and find the deficiency in the central atom and then start moving around lone pairs in the peripheral atoms one at a time. In this case, they're both equal and we need 2, so we just did them both at once. But you want to do them one at a time to go ahead and fill up your octet in the central atom. And once you do that, you're done. Now, I want to elaborate on the asterisk I had labeled a little bit earlier, which is that period 2 elements, carbon, nitrogen, oxygen, and fluorine, cannot expand their valence. They can never have more than 8 valence electrons. So you don't ever want to try to add more bonds than are possible in order to make other peripheral atoms happy. Other kinds of atoms can expand their valence, and we'll talk about that more later on, but it's important to note you should never have more than 4 bonds to a period 2 element under any circumstances. So I want to go ahead at this point and do some more examples to really get the hang of this, because drawing the Lewis structures can be a bit tricky. The first molecule I want to take a look at is phosphine, or pH3. The first choice we must make, as always, is what the central and peripheral atoms are, and I'm not going to write it down formally because it's just a choice. So in this case, hydrogen is the smallest atom and it must be peripheral. So in this case, hydrogen will be peripheral and phosphorus will be central. There's really no choice. The next thing we want to do is we want to go ahead and draw the valence electrons on the atomic symbol of each element. So in this case, phosphorus is going to have 5 electrons, just like nitrogen does, 2 pairs and 1 lone, and hydrogen is just going to have its 1 lone electron. We want to go ahead and position the peripheral atoms now around the central atom. And remember, we're going to have to split up those lone pairs to match the unpaired electrons on the hydrogen. So it's going to look something like this. We're going to go and pair first the lone electron on the phosphorus with 1 hydrogen, and then split one of the phosphorus lone pairs and pair each of those electrons with a hydrogen respectively. Now that this is done and all the electrons are aligned, we go ahead and combine those lone electrons into new bonds. Right? So we go ahead and combine those new electrons into bonds, and we go ahead and check whether or not we have full valence shells. Hydrogen can only ever take 1 bond, so those are fine. And in this case, phosphorus now has 2, 4, 6 electrons in its bonds and another 2 electrons as a lone pair. So that is a happy structure, and that is therefore the Lewis dot structure for phosphine. That's it. The next molecule is going to be OF2. It's a little bit different than we see usually because we have 2 very electronegative atoms. However, as usual, the more electronegative atom and the one that's more numerous is going to be our peripheral. So in this case, that will be fluorine. Fluorine will be our peripheral and oxygen will be our central. So we'll go ahead then and draw our base electron pairs. Oxygen will have 6, no unpaired electrons in the Lewis structure, 2, 2, and 2, with a nice gap there. And fluorine will have 7, 2, 2, and 2 paired, and 1 unpaired electron. So we want to go ahead and position these now. Fluorine being the peripheral atom and having an unpaired electron, we'll need to split some of the paired electrons in oxygen. So we go ahead and arrange the fluorines around the oxygen, giving the O, or rather splitting the pair in the O to give 2 unpaired electrons, which will line up nicely with the fluorine's unpaired electrons. We go ahead then and combine those unpaired electrons into a new bond, and we get the following structure for OF2. We go ahead and check our octet then, and we find, well, oxygen has 2, 2 in lone pairs, and 2 and 2 in bonds to give it 8, and fluorine has 6 and 2 in terms of lone pairs and bonds, so it also has 8. It is happy. Now, to do an example with some higher order bonds, we're going to look at the N2 molecule, diatomic nitrogen. In this case, there's no choice between central and peripheral because it's just a diatomic molecule, so we just go straight ahead and we draw our 2 base electron pair structures. In this case, we go ahead and align them such that the nitrogen lone electrons are paired up with one another. Pretty straightforward, just like we've been doing. The unpaired electrons line up with unpaired electrons from the other atoms. We go ahead then and combine those into a single bond straight away. But in this case, the nitrogens are not happy. They do not have enough valence electrons. Each nitrogen only has 6. So we need to shuffle some of them around. Let's go ahead and shuffle from one nitrogen first. So we're going to go ahead and move some electrons from the left nitrogen first. And we're going to take 2 of those electrons, one lone pair, and combine it into a double bond. That changes nothing for the left nitrogen. It still has 4 electrons. But now the nitrogen on the right is happy. It has 8, 4 and 4 in bonds and lone pairs. But we need to now make the left nitrogen happy, so we'll go ahead and we're going to take one of the lone pairs from the right-hand nitrogen and move it into the center bond to give us one more bond. Now, with this nitrogen triple bond, we see that each nitrogen now has 8 electrons, 3 bonds, which gives 6, and a lone pair for 2 electrons, giving a total of 8. This is the complete Lewis dot structure for diatomic nitrogen. So with that, we've actually reached the end of the content for this video. Thank you guys so much for watching, and if you enjoy what you saw, please like and subscribe to the channel. Make sure to check out our other videos in the chemistry playlist to learn more, and if you're looking to branch out, check out our other science playlists. See you next time!